Heat of Transformation, Lecture 3 and Lecture 4 of Calorimetry. So in Lecture 1 and Lecture 2, we have seen what is the meaning of heat, internal energy, temperature, different scales of temperature, how to convert one scale of temperature into another scale of temperature. Then we have seen the meaning of specific heat and heat capacities. Like when you give the heat to some object, then the temperature is raised and we can find how much heat is needed by the quantity called heat capacity or specific heat. In the present two lectures, we will explore the topic of heat of transformation. You know, whenever the matter undergoes a change in its state, like from solid to liquid, from liquid to gas, so heat is absorbed or heat is evolved. And this change of heat or heat is called heat of transformation. Okay. So basically in this lecture, we are going to study what is the meaning of heat of transformation, how to do the problems related with the heat of transformation. We will see different mixture equilibrium problems like ice water, steam water, and all the three states steam, water, ice. And then we will see the problems when the question involves variable specific heat and variable heat capacity. Okay, so these are the topics which are going to be covered in Lecture 3 and Lecture 4. One thing I recommend, if you haven't watched Lecture 1 and Lecture 2 of Calorimetry, so before proceeding with the present topic, better watch Lecture 1 and Lecture 2 of Calorimetry, then only you can have a very smooth flow in the present lectures. Now let's see what is the role of the heat supplied to any substance. So when you are supplying the heat to any object, the heat can play its role in different domains. Okay, one of the thing which is very common notion for everybody is the change of temperature. In fact, you know, we observe the absorption of heat by the increase of temperature. If some temperature is increasing, we are saying the object is being heated up. So one of the role of the heat is to change the temperature of the substance. Got it? And how it is done? You know, the particles of the substance are in random motion. So they have some average kinetic energy. When you give the heat to the object or the substance, this average kinetic energy is increased. So when this average kinetic energy is increased, the temperature of the object is increased. Okay. So this is one of the role of the heat. It can change the temperature of the substance. To illustrate, suppose you have some sample of water in the container and it is being heated up. So the temperature of the water will increase. Now the second role of the heat, which you will explore much in detail in gaseous state, it is possible that heat does not affect the temperature. Any process where temperature is constant is called isothermal process. I repeat, any process where the temperature is constant is called isothermal process. Okay, so it is possible that there is no change in the temperature and heat does work. It is converted into work. Okay, like the work done on the gas in isothermal condition. Isothermal, I told you, isothermal means constant temperature. So this is another role of the heat which heat can play. And the third role of the heat, where the heat can be utilized, is it does not affect the temperature but change the phase. Phase means state. Phase means state. Okay. State means solid, liquid, gas. These are the three common states of any matter. So one of the possible role of heat is that it does not affect the temperature but change the phase or state of the substance, like melting of ice at 0 degrees Celsius. Okay, so in the present lecture we are going to focus on this role of heat, how it changes the state of the substance. Okay, it can, you know, solid can be transformed into liquid or liquid can be transformed into gas, and the reversal processes. And whenever the change of the phase takes place, it takes place at a constant temperature. It means there is no change in the temperature. That's what we have written. The heat in this process is not affecting the temperature. Getting the point? So like when ice is melting at 0 degrees Celsius, when ice is melting at 0 degrees Celsius and water is being formed, then water is being formed at also at 0 degrees Celsius. There is no change in the temperature when the phase or state of the matter is changing. Got it? Now let's see the change of phase or state. As I told you in the present lectures, we are going to focus on this role of the heat, how it is changing the phase or state. When the matter undergoes a change in state or phase, the heat exchange do not produce change in temperature. This I told you right now. Whenever there is a change in the state of matter and there is exchange of heat, means either the matter can absorb heat or it can evolve heat, and this transfer of heat does not bring any change in temperature. So we can say that the change of the phase takes place at a constant temperature. Got it? Now if the temperature is not changing, so where this heat is going? So as I told you right now, when the temperature gets changed, when the average kinetic energy of the particles is changed. If the change of phase is taking place, if the change of state is taking place and the temperature is not changing, so surely you can say there is no change in the average kinetic energy of the particles. Because if the average kinetic energy of the particle will change, then the temperature will surely change. So there is no change in the average kinetic energy of the particle. So where the heat is being utilized in two things: overcoming the intermolecular forces, okay? Like when solid is getting converted into liquid. So the heat is being utilized in overcoming the intermolecular forces and then changing the arrangement of the particles. So this is basically, this is what is happening in change of phase, okay? Note, the heat during phase change does not affect the average kinetic energy of particle. That is why temperature remains constant. This already I told you. So this is how the heat is utilized when it is changing the state of the matter. Got it? Now let's see this pictorial way, how there are three common states of matter and there is a fourth state called plasma. Okay? So when the solid get converted into liquid, this is called melting, and liquid get converted into solid, this is called freezing. When the liquid get converted into gas, the process is called vaporization, and the vice versa, when gas get converted into liquid, the process is called condensation. And when the solid get directly converted into gas, so this process is sublimation, and when the gas get directly converted into solid, this is deposition. And as I told you, these are the three states which are the common states of matter in your syllabus. There is one more state, plasma, and when the gas get converted into plasma, it is called ionization, and when the plasma get converted back to gas, this is called deionization. Okay, so you can make this figure and the name of the different processes. Okay, you can still the screen and make the figure. Okay. Now see, plasma is not in your present syllabus, so we will have a brief description and brief idea, introductory idea about what is plasma. Plasma is an electrically conducting medium. You can say it is a fourth state of matter. Plasma is distinct from solid, liquid and gas. Got it? So it is an electrically conducting medium in which there are roughly equal number of positively and negatively charged particles. So in plasma, there are roughly equal number of positively and negatively charged particles produced when the atoms in the gas become ionized. Like if you say sun, the sun is mainly composed of plasma. Okay, the composition of sun is mainly plasma. Okay. Now let's see, as I told you, when the phase is changing, there is no change in the temperature. So if you see the variation of temperature with heat given. So suppose we have the state solid, okay, and you are giving the heat and you see the temperature is increasing. Can you see? So it is a linear graph which is telling that till this point as the heat is given, as you are increasing the supplied heat, the temperature is also increasing and the state is same. There is no change in the state. Now see, then the graph becomes horizontal, and now when the graphs become horizontal, you can simply conclude that heat is given because the graph is going ahead. Can you see? The graph is going ahead. It means there is a continuous supply of heat. the supply of heat is not stopped, but there is no change in the temperature. The graph is horizontal, the temperature is constant. So this process is representing the change of the state. And this process, when the solid is getting converted into liquid, it is called melting. And if the liquid is getting converted into solid, it will be called freezing. And the temperature at which this process takes place is called the melting point. Got it? This is called the melting point. Okay? Now, at this point, whole of the solid will be converted into liquid. Here you can say solid and liquid coexist. Here only solid is there. Now whole of the solid get converted into liquid. The change of the state has been completed. Now you are giving further heat. Now as you are giving further heat, again the temperature starts rising. Now heat is playing its role in increasing the temperature. Can you see? It is increasing the average kinetic energy of the particle. And again the graph becomes linear, suggesting that with the increase of the heat, the temperature of the substance is increasing. Now, there comes a temperature called the boiling point, where the liquid starts getting converted into gas. And since again we have a phase, something you can say, a change of phase. So with the supply of the further heat, there is no change in temperature. So again the graph becomes horizontal and the liquid is getting converted into gas, and there comes a point where whole of the liquid get converted into gas. And now if you are further giving the heat, now the gaseous state will have an increase of temperature, a linear curve. So this is how we have a graph, a curve of the temperature with heat. In the solid, the temperature is increasing. On further supply of the heat, melting takes place. The graph becomes constant, no change in temperature. Whole of the solid get converted into liquid. Now the liquid form, if you are supplying the heat further, the temperature is increasing. Now we reach a temperature called the boiling point. Again the graph becomes flat, no change in temperature with the further supply of heat, and the liquid is getting converted into gas. And when the whole liquid get converted into gas, again the temperature is linearly increasing with the supply of further heat. Got it? So whenever your graph is flat, you can say that is corresponding to melting point or boiling point. Now let's see what is the meaning of heat of transformation, or why it is also called latent heat. Now see, we will be talking about three states: solid, liquid, gas. Okay? And already I told you, we have seen the diagram, the name of the different processes. Now see, when solid get converted into liquid, it absorbed heat. Okay? It takes heat. So I can say plus heat. Plus heat means the system is taking the heat. In the same way, when liquid get converted into gas, it will absorb heat. And when the gas get converted into liquid, it will release heat. Minus means release, and plus I am denoting absorbed. Okay? And when liquid is getting converted into solid, it will release heat. Now, in these processes, we have seen in detail, in these processes, the role of heat is to overcome the intermolecular forces. The heat is playing no role in changing the temperature. Now, from a common notion, we think that when an object is absorbing heat, there must be increase in temperature. So here what is happening, though the object is absorbing the heat, but there is no change in the temperature. So virtually it seems that the object is not heated up, virtually, from a common man point. Because a common man point, a layman perception is that when the object is heated up, there must be a change in temperature. So if you are giving the heat, the question is where the heat is going, as there is no change in the temperature while the phase is changing. So it is like a hidden heat. That's why it is named as latent heat. Latent means hidden. Okay? So why heat of transformation is also called latent heat? Because in heat of transformation, there is no change in the temperature, and usually we perceive that if there is a transfer of heat between the object and the surrounding, then there must be a change in temperature. Got it? Now same, when we talk about the latent heat, so there are two kind of latent heat. Latent heat of fusion LF and latent heat of vaporization LV. Okay? Now see, what is the meaning of latent heat? It is basically the heat needed to change a unit mass of the matter from one state to another. So if suppose this is state 1 and this is your state 2 and M mass is changing and the heat needed is Q. So the latent heat will be Q by M. Got it? The formula for the latent heat will be Q divided by M. So what will be the unit of latent heat? Your unit will be joule per kg, or you can write calorie per gram. Anything that is a unit of heat divided by unit of mass. So latent heat is what? The heat needed. The heat needed to change a unit mass of a substance from one state to another at a constant temperature. Of course, you know, when there is a change of phase, there is no change of temperature. So this change is taking place at a constant temperature. Now, if you know the latent heat, you can write Q is equal to what? ml. Correct? And already, as we did in lecture 1 and 2, we throughout our thermodynamics and calorimetry, Q will denote the heat absorbed, and it is not necessary that heat is always absorbed. So we have seen when you are taking the model where Q denotes the heat absorbed and Q comes to be positive, then heat is actually absorbed, and if Q comes to be negative, then heat is evolved. Remember? So, you know, right now we have seen when the solid is getting converted into liquid, heat is absorbed. Correct? So here, for this process, the latent heat is positive, because in our latent heat formula, you are writing Q is equal to ml. So if L is positive, you are taking L as the positive value, so Q will come to be positive, which will denote what? Heat is absorbed. And if you are taking L as negative, then Q will be negative, which is telling what? Heat is evolved. So when the solid is getting converted into liquid, when the melting is taking place, your latent heat is positive. When the liquid is getting converted into solid, heat is evolved. So in this process, your latent heat is negative. And this is called heat of fusion. What? Heat of fusion. So when solid is getting converted into liquid, your latent heat will be plus LF. And when liquid is getting converted into solid, your latent heat will be minus LF. Got it? So if your ice is melting, so you will take the latent heat as plus LF, heat of fusion. If water is being frozen, your latent heat will be minus LF, which is suggesting that in this process, heat will be evolved. In the same way, when liquid and gas are taking place, transformation of the state, here we know the heat of transformation is called heat of vaporization, LV. Now when the liquid is getting converted into gas, heat is absorbed, so latent heat we must have a positive value. So L is taking as a value of LV, and when gas is converted into liquid, heat is evolved, so latent heat will have a negative value, so L will be taken as minus LV. Got it? So these are the sign of the latent heat according to the convention that we will use the model, heat absorbed model. So solid liquid LF, liquid gas LV, gas liquid minus LV, liquid solid minus LF. Got it? And whenever you need to find how much heat is absorbed, apply this formula, Q is equal to ml, and put L with proper sign, positive or negative. So Q will come out to be with proper sign, positive or negative. A positive Q will suggest heat is absorbed, A negative Q will suggest heat is evolved. Got it? Let's see your booklet ABX. Already you got the hard copy of the booklet on calorimetry ABX2. Take it out and see question number 2. A small electric immersion heater is used to boil 136 gram of water for a cup of instant coffee. The heater is labeled 220 watts. Calculate the time required to bring this water from 23.5 degrees Celsius to the boiling point, ignoring any heat loss. Now see, whenever we apply the conservation of energy equation, we know if you are taking some system and in the system there are energy changes, say delta Q, change in the potential energy delta U, and change in the kinetic energy delta K. And externally some work is done, say sigma W, and some heat is supplied by external agent, say sigma Q EXT. See, already I told you there is a difference between this heat and this delta Q. This delta Q is the sum of heat absorbed by internal objects, correct? That means the objects within the system. So if there are 3 objects, you can write delta Q will be Q1 plus Q2 plus Q3, taking the convention of heat absorbed. Of course, some Q will be positive, some Q will be negative, depending on whether the heat is actually absorbed or the heat is evolved. This delta Q, sigma Q external is the external heat supplied, okay, and this is the total work done by external agents, correct? Total work done by the external agents. Now in this problem we have a small electric immersion heater which is boiling 136 gram of water for a cup of instant coffee. The heater is labeled as 220 watts. Now see the first key point. There is a rating of the heater which is in watt. So that is the power supplied by the heater. How much? I guess it was how much? 220. Okay. So we got 220 watt. Now this heater will be doing the work, or you can say will be supplying some heat. Okay, because of this, either you can say heater is doing some work, or you can say heater is supplying external heat. That means the energy supplied by the heater can be attributed either to as the external work or to as the external heat, but you cannot attribute it to both the quantities, okay? So say in a time t seconds, if you are attributing this energy as the external work by the heater, so you can write the work done by the external agent will be, of course we know work is P into T, so you can write 220 into T, okay? Or if you are attributing it to the external heat, so you can write external heat is again P into T, that is 220 T. That is your choice in which sense you want to attribute this power of the heater. Correct? You can attribute it as the work, or you can attribute it to the external energy supplied, external heat supplied, okay? Now let us take the system as 136 gram of water at 23.5 degrees Celsius. So my system, which the system is 136 gram of water the initial temperature is 23.5 degrees Celsius, and the final temperature we have to bring it to the boiling point, that is 100 degrees Celsius. So delta T will be Tf minus Ti. So we'll get 100 minus 23.5. So we'll get 76.5 degrees Celsius, correct? So this is the change in temperature of the water from 23.5 to 100. Okay, and you are given the specific heat of water is 4200 joule. So of course, when you are bringing water from this much temperature to 100 degrees Celsius, it will absorb the heat, and the heat absorbed by the water will be the mass of the water, specific heat of the water multiplied by delta T. So this is 136 into 10 power minus 3 kg. Say I'm putting the mass in kg, and now you are putting this in 4200 joule per kg degree Celsius into 76.5 degrees Celsius. Degree Celsius is cancelled away, kg is cancelled away. So you'll get 136 into 4200 into 76.5. So you'll get 4.36 into 10 index 4 joule. Okay. So this is the heat which is needed by water to raise its temperature from 23.5 degrees Celsius to 100 degrees Celsius. Now apply the conservation of energy. There is no change in the kinetic energy, there is no change in the potential energy. So you can write the total change in the heat energy of the system is the total work done by the external agent, and I am attributing this to the work, so I am not counting it in the external heat, and this is simply the heat absorbed by water is the work done. So you'll get 4.36 into 10 power 4 is 220 into T. So T will come to be how much divided by 220? So you'll get 1.98 into 10 index 2 seconds. Okay, you can convert it in minutes. This is the answer in seconds. So further divided by 60, you will get 3.3 minutes. So time will come to be 3.3 minutes. Okay, so this will be the time taken by the heater to raise the temperature of water from 23.5 degrees Celsius to 100 degrees Celsius. Got it? Let's see what is water equivalent. See, first of all, understand that water equivalent is the property of a particular object. So when we use the word water equivalent, we associate it with some object like the water equivalent of cup, water equivalent of beaker, water equivalent of rod, so on and so forth. And water equivalent will give you the equivalent mass of water that would take the same amount of heat as needed by that substance or object to change the temperature by same amount. Okay. So what it means, suppose you are being told the water equivalent of a beaker is 100 grams. See the language. The water equivalent of beaker is 100 grams. Find the heat needed to change the temperature of beaker by 20 degrees Celsius. So you need to change the temperature by 20 degrees Celsius. And the water equivalent is 100 grams. What it means? It means now you forget the beaker. Simply forget the beaker. And think instead of beaker there is 100 grams of water. Okay, just think there is 100 grams of water. So the amount of heat needed by this much of water to change its temperature by 20 degrees Celsius will be the amount of heat needed by this beaker to change its temperature by 20 degrees Celsius. So if you are forgetting the beaker, just visualize the model in which there is 100 grams of water. So you can find heat mc delta T. So mass will be 100 gram. Specific heat of water is 4200 and multiplied by 20 in joule. This will be the answer. Got it? So I guess now it's clear. Whenever you are given the water equivalent of any object, you can simply think it like water. Take the mass of the water and apply the formula Q is equal to mc delta T, keeping the value of C as the specific heat of water. Okay. Now let's see the problems when we bring the objects in contact or bring the objects such that heat flows between them even if they are not in contact. or bring different phases, like you are passing the steam in a container with water. You are putting ice in some container where there is already some water. So in all such problems, the heat will flow till the system attain a final common temperature. Okay, the heat will flow till the system attain a final common temperature, and that final state is called the thermal equilibrium. So suppose you are passing the stream in a container which contains some water. So heat will get transferred between steam and water till the system will attain a final common temperature. Got it? Now see, we will see problems of mixture like ice and water, steam and water, and as already we have seen in the introduction of the lecture, third will be steam, water and ice. Ice and water, steam and water, and steam, water, ice. So let's see when we have problems related to ice and water mixture. Now suppose there is x gram of ice at 0 degrees Celsius, and just focus on the fundamentals. Okay, just keep the pen aside and focus on the fundamental. We have x gram of ice at 0 degrees Celsius and y gram of water at t degrees Celsius. Okay, of course your t will be something between 0 and 100. Now we have to find two things. What will be the composition of the final system? Okay, what will be the composition of the final system? Composition of final system means whether the final system will contain ice, water, whether it will contain only water, so on and so forth. Okay, and number two, what will be the temperature of the final system? Of course, heat will flow between these two components, ice and water, till they attain a common temperature. So see how we will approach such problems. See, one thing is for sure, here the initial temperature is 0 degrees Celsius, here the initial temperature is t degrees Celsius. So your final temperature will be something like between 0 degree and t degree. Whatever will be the temperature of the equilibrium state, it will be between 0 and t degree. Okay. Now see what we will do, how we are going to approach such problem. Number one, step one. Assume that y gram, whatever gram or kg, y mass of water at t degrees Celsius comes to y mass of water at 0 degrees Celsius. Okay, now you see the temperature is decreasing, and if the temperature is decreasing in this process, heat is released. Okay, so basically when water is getting low in temperature, in this process heat will be released. So let us find the heat released. Let Q1 be the heat absorbed. So Q1 will be the mass of the water, specific heat of water, change in the temperature. So we'll get mass of water, specific heat of water, 0 minus T. So we'll get minus mass of the water, specific heat of water into T. Of course, this Q1 will come to be negative, which is suggesting that heat is evolved, correct? So at the very first step, do what? Find the heat absorbed. See my language, I am saying find the heat absorbed. Your heat absorbed will come to be negative. Find the heat absorbed in changing the temperature of complete whole water from T degree to 0 degree. And since it will come to be negative, you can write heat released is modulus of Q1, correct? You can take the modulus value. Now you are talking about heat released. So it will be the modulus of Q1. Okay. This much heat will be released when the water cools down. Now step 2. Let us find the heat required to completely melt the ice at 0 degrees Celsius. Okay, now we are finding what will be the heat needed to completely melt the ice at 0 degrees Celsius. So we have some mass of ice at 0 degrees Celsius and it's getting to water at 0 degrees Celsius. Solid is getting converted into liquid. So L will be plus LF. Say heat absorbed is Q2. So this will be mass of the ice into LF. So you can write heat required to completely melt the ice is what? Modulus of Q2. Of course, Q2 will come to be positive value because here the heat is absorbed. Okay, so you got two things. Now you are clear. You got what is the heat released and what is the heat absorbed. Now there will be three cases. Case 1, three possibilities are there. Q released is precisely equal to Q required. So your whole of ice will melt. So your final state will only be water, nothing else, at 0 degrees Celsius. Got it? This is the first possibility. If both the heats are equal, so heat is just sufficient to melt the whole ice. So your final state will just consist of your water at 0 degrees Celsius and there will be no ice. Case 2, heat required is less than heat released. Okay. Now just see from the common sense. The heat needed to melt the whole ice has a lesser value than the heat released. So you suppose 1000 joule of heat is released and to melt the whole ice, say we have 500 joules of heat. So of course whole ice will get melted. So what it implies that whole ice will be melted. Now what will happen? After the whole ice will get melted, there will be some excess amount of heat still left. So after melting, we have some excess amount of heat. How much? Q released minus Q required, correct? So, since the heat released is more than the heat required to completely melt the ice. So, of course, it will melt the ice and there is excess amount of heat. And we have, since, this heat has been transformed in bringing some initial sample of water, that was Y mass of water from T degrees Celsius to 0 degrees Celsius and X mass of ice to X mass of water at 0 degrees Celsius. So now your present system is only water and how much mass? X plus Y at 0 degrees Celsius, correct? After melting, this is what is the system. We have only water at 0 degrees Celsius of how much mass? X plus Y. And we also have excess heat. Now this excess heat will raise the temperature of water from 0 degrees Celsius, correct? Because there is still some heat left. So what it will do, since already the whole ice has been melted, so what will be the role of this excess heat? This excess heat will be raising the temperature of this much water. So let the final temperature be T naught. So you can write Q excess is equal to mass of the water, that is X plus Y, specific heat of water T naught minus 0, and you will get what? T naught. And of course your T naught will be greater than 0 degrees Celsius. Okay. So if your required heat is less than, got it? The second case is what? If the heat needed to completely melt the ice is less than the heat released, then your whole ice will be melted, number one. Number two, The water at 0 degrees Celsius will get elevated in the temperature with the excess heat, and your final temperature of the system will be something more than 0 degree. Now you can judge intuitively what is your case 3. Now case 3 is Q required is greater than Q released. So of course, more heat is needed to completely melt the ice than the heat released. So of course, whole ice will not melt. Whole ice will not melt. So your final state will have what? It will have ice plus water at 0 degrees Celsius. And what is the mass of ice that will be melted? So can you write Q released divided by heat of fusion. So this will be the mass of ice that has been melted, correct? So in this case, your final temperature will be 0 degrees Celsius and we have ice and water, okay? So you can see we got 3 cases. We have seen the analysis of 3 cases. Number 1, if both the heats are equal, whole of the ice will get melted. The final state will be at 0 degree. If required heat is less than the released heat, again the whole ice will be melted. The final state will be simply water at a temperature greater than 0 degree. And if the required heat is greater than heat released, whole ice will not get melted. The final state will be ice plus water at a temperature 0 degree. So you can make the flow chart like this, okay? Now let's see an illustration. 150 gram of ice is mixed with 100 gram of water at a temperature of 80 degrees Celsius. See, in such problems, do one thing. First of all, represent the whole process in a flowchart form. So you will clearly visualize what is happening. So we have what? 150 gram of ice at 0 degrees Celsius. It must be given at 0 degrees Celsius. If nothing is given, you will take 0 degrees Celsius. Otherwise, some other temperature might also be given, like -5, -10. We will see later what will happen when initially the ice is at some other temperature, say -5, -10. So we have 150 gram of ice at 0 degrees Celsius, and we have 100 gram of water at how much? 80 degrees Celsius. Got it? Okay, now let's see. The latent heat of ice is given and the specific heat of water is given. Assuming no heat loss, the amount of ice that does not melt. So right now we have seen the approach. Let us apply it. So I've told you step 1. Just imagine your water is getting lowered in temperature and you got 100 gram of water at 0 degrees Celsius and say the heat absorbed is Q1. So mass of the water, specific heat of water, delta T. So I'll get 100 gram, and what is 1 calorie? Since it is in gram and it is in calorie per gram, so we need not to convert it in kg. 0 minus 80, so I'll get minus 8,000 calorie. Of course, you're getting a negative sign, which is suggesting that heat is evolved. So I told you, now we have to write Q released, so that will be modulus of Q1, so it will be 8,000 calorie, okay? So this is the amount of heat that will be released. Okay, now let's come to step 2. Initially the ice is at 0 degree. Let us assume that the whole of the ice get melted and you get 150 gram of ice get converted into 150 gram of water at 0 degree, and the heat absorbed is Q2. Since it the change of state, so Q2 will be mass of the ice multiplied by latent heat of fusion. So mass is 150 into what? Latent heat of fusion is, and we will take of course plus LF because solid is getting converted into liquid, so L will be plus LF. And you are given, I guess, latent heat of fusion 80 calorie per gram, so I'll get 150 into 80. 12,000. Okay, so you'll get 12,000 calorie. The heat required is modulus of Q2, that is 12,000 calorie. The heat required to melt whole ice is 12,000 calorie, and the heat is that is releasing in the process is 8,000 calorie. The heat required is greater than heat released. So therefore, whole ice will not melt. Clear? We have seen the analysis right now. So your final state will be what? Your final state will consist of ice plus water at 0 degrees Celsius, and we have to find the mass of ice which has been melted. So that is Q released divided by LF, that is 8,000 calorie by 80 calorie per gram. So you'll get 100 gram. So 100 gram of ice will get melted. Correct? 100 gram of ice will get melted. So what will be the amount of ice that will not get melted? So total amount was 150 gram, out of which 100 has been melted. So of course, so 50 gram will remain unmelted. So answer will be 50 gram. Got it? Perfect. Now see the next problem. Your ABX booklet 2, question number 8. 300 gram of water at 25 degrees Celsius is added to 100 gram of ice at 0 degrees Celsius. Find the final temperature of the mixture. I guess you will be able to solve this problem. 100 gram ice at 0 degrees Celsius and 300 gram of water at 25 degrees Celsius. So let Q1 be the heat absorbed in converting in 300 gram of water at 0 degrees Celsius, and let Q2 be the heat absorbed in melting the whole 100 gram of ice at 0 degrees Celsius. Correct? So you'll get the value of Q1 and Q2. What will be Q1? Mass of the water, specific heat of the water into delta T. So mass is 300 gram, specific heat is 1, and you'll get minus 25. So this will come to be 300 into 25. We'll get minus 7.5 into 10 power 3 calorie. So Q released is modulus of this one. So we'll get 7.5 into 10 power 3 calorie. Now let's see how much heat is needed to completely melt the ice. So it will be mass of the ice into latent heat of fusion. So mass is 100 gram and the heat of fusion of ice is 80. So we'll get what? 8,000 calorie. That means 8 into 10 power 3 calorie. So heat required is this much. Modulus of Q2, that is 8 into 10 power 3 calorie. So clearly you can see heat required is more than heat released. So of course your whole of the ice will not melt. So your final state will be what? Your final state will consist of water plus ice at 0 degrees Celsius. Got it? And the demand of the problem was simply what will be the final temperature of the mixture. So answer will be 0 degree Celsius. Got it? Now see the next problem, ABX 2 booklet, question number 10, that is from JEE Main 2023. Okay, the problem is from JEE Main 2023. Heat energy of 184 kilojoule is given to ice of mass 600 grams. So we have ice, 600 gram of ice at minus 12 degrees Celsius. So this is the state of the substance we have, and you are given how much energy? External energy is being given, and since heat is given, so we'll take plus. So system absorbs external heat of 184 kilojoules, and we have to find what will be the final state. See, this problem is different from the previous problem. What was happening in the previous problem? No external heat was involved, correct? What was happening in previous problem? No external heat was involved. The heat that has been released by cooling down the water, that heat being utilized in melting the ice, and then if further heat was available, then raising the temperature of the water so formed. In this problem, there is only ice, no water. Number one, first difference. There is only ice, no water. And number two, there is some supply of external heat, 184 kilojoule. Okay, now let's see. We have to see whether the whole ice will be melted or not. Let Q1 be the heat absorbed when your 600 gram of ice comes at 0 degrees Celsius, correct? So let us find Q1. So since it is the change of temperature, not the change of state, so we'll apply the formula mass of the ice is specific heat of ice into delta T. And I guess some data are given in the problem. The specific heat of ice is 222.3 joule per kg. So also mass we will take in kg. So 600 into 10 power minus 3 into 2222.3 joule per kg Kelvin, and this is in kg, into 0 minus of minus 12 will be 12. And you know delta T in Celsius is same as delta T in Kelvin. You need not to worry about that. That specific heat is given in per Kelvin. So why we are writing the change in temperature in Celsius? The change in temperature in both the unit is same. So we'll get 600 into minus 3, 2222.3 into 12. So we'll get 1.6 into 10 power 4 joule. Okay. This will be your energy, and of course, so this energy is coming to be positive, so heat is absorbed. So of course this value is less than the total heat supplied by the external agent. Clearly you can see Q1 is less than Q external. So excess heat is there. Getting my point? There is some excess heat. So not only your ice will come at 0 degrees Celsius, now ice will start getting melted. And now we don't know how much amount of ice will get melted. Okay, so let's see what is the excess amount of heat left. So this is the heat supplied by the external agent minus the heat needed to raise the temperature of the ice. So I'll get 184 kilojoules minus 1.6. So we'll get 1.68 into 10 power 5 joule. Okay, this is now the excess heat after bringing your ice to 0 degrees Celsius. Now let's see how much mass can be melted by this excess heat. Let m0 kg of ice can be melted by this excess heat. Okay, I don't know what will be the value of m0. Let's find out the value of m0. So we know Q is equal to mLF. So therefore m0 will be Q excess divided by heat of fusion. Now you will get m0 as 1.68 into 10 power 5 joule divided by, let's see what is the heat of fusion given. The value is given in the problem, I guess. So your heat of fusion of ice is latent heat 336 kilojoule per kg. Kilojoule means, so I'll get 0.5 kg, or you can say 500 gram. Okay, now see, this excess heat after bringing the ice to 0 degrees Celsius, some amount of excess heat was there, and this excess heat can melt at the most 500 gram of ice, not more than 500 gram. What amount of ice we have? We have 600 gram of ice. So what will happen out of this? 500 gram of ice will be melted. And form water, and 100 gram will remain as such. So 100 gram ice unmelted. And what will be the final temperature? Since we have both ice and water in the system, the final temperature will be 0 degrees Celsius. Now we can check out the options. Let's check out what are the different options. So we are given statement A, that was the problem from JEE Main 23. Statement A saying the final temperature of the system will be 0 degrees Celsius. Correct? Absolutely correct. We have seen since the final mixture is consisting of ice and water, it will be at 0 degree. Final temperature of the system will be greater than. Incorrect. B is in contradiction with A. The final system will have a mixture of ice and water in the ratio 5:1. So we have seen the mass of water is 500 gram and the mass of ice is 100 gram. So ice and water is not 5:1. Ice and water is 1:5. Yes, this option is correct. Because 100 gram and 500 gram will make a ratio 1:5. So your which option will be correct? Option B, that is the statement A and D. Okay, so your correct option will be B, A as well as D. Okay, now see the next problem, ABX2, question number 18. When M1 gram of ice at minus 10 degrees Celsius is added to M2 gram of water at 50 degrees Celsius. Finally, no ice is left and the water is at 0 degrees Celsius. Now when you are mixing these two states, then it is being told that the final state is at 0 degrees Celsius and there is no ice left. So this thing will get converted into M2 gram of water at 0 degrees Celsius, absorbing heat Q1. Again, see, every time I am using the word absorbing heat Q1. You might think why the heat will be absorbed. The temperature is decreasing, so of course heat will be evolved, no doubt. But as I see, we are using the word absorbing. So of course your heat absorbed will come to be negative whenever the heat is evolved. And here we will have M1 gram of ice. First it will come at 0 degrees Celsius, then it will get converted to M1 gram of water, since it is being told that no ice is left. So of course your whole ice will get converted into water at 0 degrees Celsius, and this is your final state. So here say the heat absorbed is Q2 and this is Q3 and no external heat is supplied. So system is isolated. So what will be Q1? We'll get mass of the water, specific heat of water into delta T. So Q1 is mass of the water is M2. The specific heat of water is how much? 1. And delta T will be 0 minus 50. So we'll get minus 50 M2. Now I can see the heat absorbed is coming to be negative, which is suggesting that actually the heat will be evolved. Q2 will be what? Q2 is again the change of temperature, not the change of state. So the mass of the ice, specific heat of the ice, delta T. So mass of the ice is M1, the specific heat of the ice is given in the problem, 0.5, and your delta T will be how much? 0 minus of minus 10, that is 10, so I'll get 5 M1, correct? And what is your Q3? That is the change of the state from ice to water. So I'll get mass of the ice into latent heat of fusion of ice, that is M1 LF. Okay, so we got inside the system, I'm taking the system as water plus ice. Is there any external work? No. Is there any external heat supplied? No. Change in potential energy? No. Change in kinetic energy? No. So therefore, sum of the internal heat absorbed will be 0. Sum of the internal heat absorbed by the conservation of energy equation, this will be 0. So therefore, Q1 plus Q2 plus Q3 will be 0. So what was Q1? Minus 50 M2. What is Q2? Plus 5 M1. What is Q3? M1 LF will be 0. So what you will get? You will get M1 LF is what? 50 M2 minus 5 M1. So LF will be 50 M2 divided by M1 minus 5 M1 by M1 will be 1. This will be the answer. So this is the latent heat of the ice, 50 M2 by M1 minus 5, correct? Now see the next problem, your booklet AVX2 question 21, that is a problem from IIT 2003. We have 2 kg of ice at minus 20 degrees Celsius. Here see, the initial temperature of the ice is not 0 degree. Can you see? The initial temperature of the ice is not 0 degrees Celsius, it is minus 20 degrees Celsius. And it is mixed with 5 kg of water at 20 degrees Celsius. Okay, fine. In an insulating vessel having a negligible heat capacity, so vessel will not absorb any heat, that will be neglected. Calculate the final mass of water remaining in the container. It is given that the specific heats of water and ice are this and this, while the latent heat of fusion of ice is this. Okay, now see. We will do the same thing. First of all, see step 1. I will calculate the heat absorbed in changing the temperature of the water from 20 degree to 0 degree and say the heat absorbed is Q1. Of course, Q1 will come to be negative. The temperature is being lowered down. That is mass of water, specific heat of water into delta T. So mass of water is 5 kg, okay. And it is given in how much? Your specific heat is given in, specific heat of water is 1 kilocalorie per kg. So I am writing this in kg, 5 kg, 1 kilocalorie per kg per degree Celsius, and delta T will be 0 minus 20 degrees Celsius. So of course we'll get minus 100 kilocalorie. Negative sign is suggesting heat is released. So therefore, heat released is modulus of Q1, that is 100 kilocalorie. Okay. Now let's see what will be the role of this much amount of heat that has been released. First, your ice is at minus 20 degrees Celsius. So for melting the ice need to get elevated in temperature up to 0 degrees Celsius. So first heat will be utilized in raising the temperature of ice to 0 degrees Celsius, correct? Let it be Q2. And your Q2 will be mass of the ice, specific heat of ice into delta T. So mass is 2 kg, and I guess the specific heat of ice is given that 0.5 kilocalorie per kg per degree Celsius. 0 minus of minus 20 will be 20. So kg will get cancelled, your degree Celsius will get cancelled. So what will get 20 into 2 into 0.5, so we'll get 20 kilocalorie. Okay. So here the heat absorbed is 20 kilocalorie and the heat released was 100 kilocalorie. So out of 100 kilocalorie heat released when the water came to 0 degrees Celsius, 20 kilocalorie heat has been utilized in increasing the temperature of ice up to 0 degrees Celsius. So what is the excess amount of heat left? Q released minus Q2. So I'll get how much? 80 kilocalorie. Now what will be the role of this excess heat? Now already we have ice at 0 degrees Celsius. So this excess heat will start melting the ice, and let us see how much ice will get melted. Let m naught kg of ice be melted. So m naught will be excess heat divided by latent heat of vaporization. So we'll get 80 kilocalorie divided by your latent heat is given for ice is 80 kilocalorie per kg. 80 kilocalorie per kg, your kilocalorie will get cancelled and will get 1 kg. So the amount of ice that will be melted by this excess heat is 1 kg. And what was the amount of ice at 0 degree? 2 kg. So 2 kg ice was there. And the excess heat is just available to melt 1 kg of ice. So what do you think? Will the whole ice be melted? No. Only 1 kg of ice will be melted. So therefore, final mixture will compose what? Ice how much? There was 2 kg out of which 1 kg has been melted. 1 kg plus water how much? So 1 kg ice melts and form water, and initially there were 5 kg of water. So we have 6 kg of water. And what will be the equilibrium temperatures in both the phases are present, ice and water? It will be 0 degree. So let us see which option will be correct. So we have to find what? Calculate the final mass of water. So the final mass of water is 6 kg. Option B is the correct option. Got it? Now same, in this lecture we have seen the calculations involving water and ice mixture. In the next lecture, we will see the calculations involving steam water mixture and steam water and ice mixture. Of course, your approach and fundamentals will be the same, only the variety of problems will differ. Okay, your fundamentals and approach will be the same. So in the next lecture, we will cover these two topics. Got it?